order to find the magnitude of couple moments m1, m2, and m3 so that the resultant couple moment acting on the system is equals to 0, we can go ahead and write our expression that the resultant couple moments will be the sum of all the moments acting on this system. In this case, we have 4 of them, and their sum should be equals to 0 based on the condition given in the problem. So let's go ahead and write each one of them in the Cartesian form so that we can later add them together. So to start, I have my couple moment m1 that is parallel to the y-axis. In other words, it will only have the y component, which we can represent it as m1j. Next, we have m2 that is acting along the x direction. However, it is pointed in the negative x direction. That's why I have negative m2I. Now for m3, it is acting in 3D space, so we have to identify the unit vector along which this moment is acting across. To do that, we can calculate the position vector where m3 lies by calculating the point coordinates of head and tail. In this case, the point coordinates of head are 2, comma negative 2 comma 1, whereas the tail lies at the origin, so it has the coordinates equals to 0 comma 0 comma 0. So to calculate the position vector, it will be the head coordinates minus the tail coordinate. So in this case, I have a position vector of 2 minus 0I plus negative 2 minus 0j and plus 1 minus 0k. This is the position vector. Now to calculate the unit vector, we have to divide this position vector with the magnitude of the position vector. So the magnitude can be represented as a square root of the x component is square, that is 2 square, plus negative 2 square plus 1 square. Simplifying, we get our couple moment m3 represented in Cartesian form as 2 over 3 m3i, negative 2 over 3 m3j, and finally 1 over 3 m3k. Now let's look at the final couple moment whose magnitude we know. Now this one also represent in the 3D space, and we are given a couple of right angle triangles so we can project it along the x, y, and z axis. So to start, I have a 150 pound fit couple moment making an angle of 45 degree with the xy plane. So taking the cos function of 45 will project it along the xy plane. Next, if we take the sine 45 function, it is going to project it along the z-axis. However, it is pointed downwards and the moment is in the clockwise direction. So the value of the z component will be 150 sine 45. Now let's go back to our cos 45 component that lies along the xy plane. We need to further resolve it along the y-axis and x-axis. Since this line is making an angle of 45 degree with the y-axis, taking the cos function will project it along the y-axis, whereas taking the sine 45 function will project it along the x-axis. In this case, the direction along the y is going towards the negative y-axis, whereas along the x is going towards positive x-axis. Now, once we have all the three components, let's go ahead and write our m4, that is 150 cos 45 sine 45i, since it is acting towards the positive x direction and it is in the counterclockwise direction, whereas the y component is negative 150 cos 45 cos 45, as it is pointed towards the negative y-axis and it's in the clockwise direction. And finally, I have the z component that is acting also in the clockwise direction. That's why I have a negative 150 sine 45k. Simplifying, we get our m4 value as 75i minus 75j minus 106k. The units for this moment is in pounds feet. Now, once we have all the four moments, let's go ahead and add them together to figure out our resultant. And as we know, the resultant is equals to 0. So let's equate their sum equals to 0. Now, to start, our m1 is just the j component, so I can just write that m1j plus negative of m2i plus 2 over 3 m3i minus 2 over 3 m3j plus 1 over 3 m3k. And finally, I have M4, which we have the actual values of, that is 75I minus 75J minus 106K. Now, once we have this, let's rearrange the expression so that I have all the I components added together, all the J components added together, and K components added together. Once we have this, we can equate the I component, J component, and K component on both sides of the equation to solve for the magnitude of M1, M2, and M3. So rearranging the terms, we get our very first terms as negative M2 plus 2 over 3 M3 plus 75 I, since all of this is multiplied with the I component. Next, I have the J components as M1 minus 2 over 3 M3 minus 75J. And finally, we have the K terms, that is 1 over 3 M3 minus 106, and that is multiplied with K, equating it equals to 0. Now, once we have separated our I, J, and K terms, we can go ahead and equate the I terms on both sides of the equation. Now, in this case, since on our right hand side we have this thing equals to 0, meaning that the I component on the right hand side is equals to 0, J component is equals to 0, and K component is also equals to 0. So we can write three expressions equating I, J, and K components. So to start, I will begin with the K as it has only one unknown and we can easily solve for our M3 value. So writing our very first expression, 1 over 3 M3 minus 106 equals to 0. Simplifying, we can get our value of M3, that is coming as 318 pound-feet. Next, let's go ahead and equate our J terms on both sides of the expression. So I have M1 minus 2 over 3 M3. Since we have already solved for M3, let's plug in that value of 318 minus 75. Simplifying, we get our value of M1, that is coming as 287 pound-feet. Now, finally, we can go ahead and equate the I terms on both sides of an equation and figure out our value of M2. So in this case, I have negative M2 plus 2 over 3 M3. Since we already know the value of M3, that's 318. Let's go ahead and plug that thing there. Plus 75 equals to 0. Simplifying, and we get our M2 value as also 287 pound-feet.